This is the third lecture on persistent homology. In this lecture, we will bring together the ideas that we have seen so far towards the problem of measuring shape, first for a point cloud, and then we will see how the filtration can be applied to study Morse functions. Let's think about a collection of points here. The points in this case come with weights, and the weights are interpreted as the radius of a disk centered at that point. So what you see here is a collection of disks with differing radii, alternately a collection of weighted points. The collection of weighted points represents some shape. So in this case, a shape that has a hole, has a single component, some protruding structures, and so on. The green edges that you see are not so important for our discussion, but just for completeness I will say what they are. So the green edges, if you notice, the green edges are between pairs of adjacent disks. This is exactly the edge of a Voronoi diagram, or the Voronoi cell of each weighted point. Like I said again, this green edges are not relevant. What is important is to focus on the union of these disks. The union of these disks represents a shape, and we would like to now measure this particular shape. We already have the necessary tools with us, except for one important tool, which is how do we represent this collection of disks. Now, why should we care about measuring the shape in terms of, let's say, for a given set of points, for example, in terms of the holes or components? Well, instead of thinking of these as disks, you can think of these points in 3D and their weights as representing the radius of a ball. These balls could be atoms, and maybe what we are studying is molecules that are represented as a collection of atoms, and the volume occupied by an atom is the volume occupied by the union of all the atoms in the molecule. Now, so far we have been talking only about points and the disks or the balls that are representing the molecule. So these representations are not very much amenable to computation, but a dual structure, which is called the nerve, the formal definition is not so important, but I will say it here. I will explain it here anyway in terms of the this particular diagram. So the nerve represents the intersections between various collections of disks, or it captures the relationship between various collections of points. So what is shown in pink in the lower left figure, you may think of it as the nerve, where every pairwise intersection between disks is represented as an edge, and triple intersections are represented as a triangle. Each disk trivially intersects with itself, so it is represented by a vertex. So the nerve is you can think of it as a graph, but since it has higher dimensional simplices, it is actually a simplicial complex. Now, this nerve is what we are going to use to study the shape of the union of disks. Now, one can show that under appropriate definitions, the topology of the simplicial complex, which is the nerve, is equal to the topology of the union of disks. Within the next couple of slides, we are going to talk about unweighted points. This is just for simplicity. Many of these analyses do work for weighted points. However, for points in low and higher dimensions, often we do not need a notion of weight. So here we have a collection of points with equal weight. And what you see is a collection of disks representing these points, and you will notice that all the disks have equal radius. Hence, hence there is no distinguishing weight for each point. And the simplicial complex that you see represents the dual of the union of disks. Now let's think about some characteristics of this shape, the union of disks. It has again one component. It has a single cycle or a tunnel that you can see at the center in white. And visually we can also verify that the homology of the union of disks of this topological space is the same as that of the nerve. So the nerve also has a single component and it has a single cycle that is not bounded. Now let's introduce the so-called Vitoris-Rips complex, which helps represent this dual for different radii. The Vitoris-Rips complex essentially is this. It represents this connectivity for different radius r. I should start by saying this is a disclaimer. This is not the nerve. This is not the nerve. It is merely a approximation of the nerve, which is why I introduced the nerve initially just to motivate. But I'm not going to define the nerve formally. I'm going to define only the Vitoris-Rips complex. The Vitoris-Rips complex is defined for a collection of points in any dimension, and the Vitoris-Rips complex VR at for a given parameter r is the collection of all. It is the collection of all simplices. So sigma are all the simplices. These simplices are represented as subsets of the point set. So this means that we are starting with S, a collection of points. We have a collection of points, and each subset corresponds to a simplex, sigma. So you collect all those sigma whose diameter is less than equal to 2r, which means that the length of the longest edge in that simplex is less than equal to 2r. Another way to think of this is as follows. So here we have a collection of points. So let me try to draw this point collection here. So you start with the point collection and you assign and you look at the parameter r, and you look at every edge, and if the edge is smaller than to R, then you insert it. So these are exactly the edges that get inserted in this particular case. It may not be a faithful reproduction of the figure on the top, but let's go with that. So here you have all the edges whose length is less than equal to 2R. So these edges go into the Vitoris Rips complex. Now I think I missed one edge. Now let's consider all triples. If all three edges are belong to the Vitoris Rips complex, then you insert the triangle as well. So similarly, you insert this triangle because all three edges are part, and then these triangles. The other triangles are not inserted because only two edges or one edge belongs to the Vitoris Rips complex. So note that the way the Vitoris Rips complex is defined, you may not be able to embed it on the plane without self-intersection. For example, if for a slightly higher value of the radius parameter R, the edge AC may also belong to the Vitoris Rips complex, and then the triangles ACB and ACD will also belong to the Vitoris Rips complex. That's fine. This is still a simplicial complex, but it can be realized in some higher dimensional space. So one can easily see that this is indeed a simplicial complex that you can verify for yourself. And this complex is called the Vitoris Rips complex. The Vitoris Rips complex is a good representation of the topology of the union of the collection of points for different values of R. Now, if we want to talk about the shape of these points in higher dimensional space, so let's assume that these points are sampled from some surface or some submanifold in higher dimensional space. So these points are merely a sample. We can use the Vitoris Rips complex to represent the space from which the points are sampled. So that is the role of the Vitoris Rips complex. However, what value of R do you choose? This is not too clear, right? And another question that is not too clear to answer is, if you have these collection of points, do they belong to two components, three components, or a single component, or are they sampled from like 10 different components, and does the collection of points represent a whole, and if yes, what is the size of that whole, and so on. So answering these questions becomes easy now that we have a tool called persistent homology. Now, what is the filtration here? The filtration is simply given by the parameter R. So as you keep increasing R, we get larger and larger complexes, VR of R, and that gives us the filtration. And we can compute the persistent homology and record it in the persistent diagram. So all holes together with their size is captured in the persistence diagram. So for example, the hole that you see right here in the middle will also be captured as a pair which will be an edge that created the cycle and a triangle that eventually filled this cycle. So that pair in the persistent diagram will capture the this large hole, and the persistence of that pair will tell us the size of this hole. So the size of all the holes is captured really well with the persistence diagram. So this is one way of studying point sets. In fact, when you consider such a point cloud in higher dimensions, the pth persistent Betti numbers, which come from the persistence diagram, the pth persistent Betti numbers, they serve as a feature descriptor. So, for example, you have 2 point clouds. You could look at the Betti numbers, the pth persistent Betti numbers for some interesting threshold of R, and use that as a feature descriptor. And you can use this to compare two different point clouds and so on. And this sort of analysis is fairly common in TDA, which often begins with a point cloud in higher dimensions. And as a first step of TDA, you do compute the persistence diagram, and then study the Betti numbers, the persistent Betti numbers from the persistence diagram. Next, we will move on to the analysis of a specific filtration. This will actually help us tie together the two ways of looking at persistence, namely from Morse functions and via filtrations. We will study the sweep approach that we saw in the first lecture on persistence. We will understand that sweep procedure via a filtration. So that is what we are going to discuss now, and conclude this lecture. So here we have a simplicial complex, and let's assume that the vertically upward direction corresponds to a Morse function f. So the triangles are laid out on the plane such that their vertices have function value in the increasing y direction. Now let's take a particular value t and look at the collection of simplices that lie below this particular t. So it consists of various vertices. Now if all three vertices of a triangle are below, then naturally we know that the triangle, the function values in the triangle also lie below t, and so it is also covered. So some of the triangles are partially covered, and some triangles are fully covered. Now as we sweep, these different triangles get eventually covered fully. But instead of this continuous sweep, we will sweep this simplicial complex by making discrete jumps, which is essentially how we build a simplicial complex using a filtration. And the different jumps are the insertions of simplices. So what we will do is, at every step of the sweep, we will insert a vertex. So when we cross t, the first event is the insertion of a specific vertex. So let's say this is the vertex that I insert. Now this vertex is inserted first, So let's give it a name. Let's say V is inserted. But as soon as V is inserted, we would like some edges and triangles that are incident on V to also be inserted. Now, how do we decide whom to insert? We know that V has several neighbors. In particular, its neighboring vertices are U and W. And naturally, VU and VW are cofaces, and VUW, the triangle, is also a coface. In fact, these cofaces are exactly what we call as the lower star. The lower star of V. So these are all the cofaces of V that have function value lower than V. Now we would, after inserting V to form a K sub I, we want to create the next few simplicial complexes in the filtration, K sub I plus 1 and so on, to K sub I plus some K, by inserting all the simplices that belong to the lower star. Now we have to be careful in what order we insert them. The only constraint is that we need to insert a face with all the faces before we can insert the a simplex. So so we have inserted V. So before we can insert a triangle VUW, we need to insert the edge UV and the edge VW, after which we can definitely insert the triangle UVW. So this filtration, since it inserts V followed by its lower star, is called the lower star filtration. Now you can see that the lower star filtration will give us this sweep over the entire simplicial complex. So when we talked about the sweep, if you recall, we talked about creators and destroyers and how to pair them. Now how do we pair the critical points here? Now when we saw the filtration, we again saw that using the cycle search algorithm, you can pair the creators with the destroyer simplices. So these two ideas come together here, but in a much simpler form. So during this filtration, how do we pair the critical points? It is sufficient to study what happens to V under the different cases, and that already addresses our question. So let's look at the regular vertex first. It is not special, but it is nevertheless very interesting. So the regular vertex is one where the lower link has a single component, and we have often used blue to indicate lower link, so I will continue to use that. We have a lower link. The upper link is irrelevant here because this is only a lower star filtration. I do insert V. So I insert V, and when I insert V, there are a few vertices that are already present even before I insert V, right? So let's give them some names. V1, V2, V3, and V4. Right. So I insert V, and when I insert V, I create a new component. So I create a new cycle. So V is a creator. V is a creator. Right. Now next I need to insert some edges. So let's say I insert one of these edges. The order in which you insert the edges is not relevant, but I will insert them in a particular order to make this diagram simple. When I insert the edge V1, I destroy a component by definition, because V was a single vertex, single component, and you connect it to the remaining part of the simplicial complex. So the edge V1 is a destroyer, and it destroys the simplex that was created by V. So the edge VV1 is already paired with V. So that's taken care of. Next I insert the edge VV2. Now VV2 is a creator. It creates a cycle, a one cycle. The cycle is V1, V2. That cycle is created when you insert the edge V2. Now next, just to make things simple, I insert the triangle. This is valid. I can insert the triangle. I insert the triangle. Now this triangle destroys the one cycle that I created just now. So the triangle is paired with, the triangle V1, V2 is paired with V2. So I proceed like that. V3 is a creator which is paired with the triangle V2, V3. And V4 is also a creator which is paired with a triangle V3, V4, which is a destroyer. Now you have already inserted V and its lower star, and in doing that we have paired all the simplices that we have inserted now. We have found pairs for all the simplices, and they are all local pairs, right? Now let's see what happens to the other cases. Let's start with a minimum, because it's simple again. So in the case of the minimum, we know that its link is, the lower link is empty. So the only thing that you have to insert is V, and it is positive. So V is a creator and it has no pair in the local neighborhood. Let's hold on to that. There is nothing else to pair, only V needs to be paired, but I don't know who to pair it with. So I leave it as it is for now. Next, let's look at a saddle. I'm going to look at a simple saddle, but the same works for multi-saddles. So a saddle has two components and has multiple vertices, maybe just one vertex or multiple vertices in the link, in the lower link. Remember, we care only about the lower link, the lower star actually. So let's do this exercise. When I insert V, V is as usual positive as before. Now I insert an edge V1. Similar to the regular case, this is negative. It destroys a component, and the edge V1 is paired with V. So far so good. Then we insert the edge VV2, which is a creator, and it is paired with the triangle, that's a destroyer. And then we insert the edge V3, which is again a creator, and then you insert the triangle, which is a destroyer, so that is paired, right? Now comes the interesting part. So you insert V4, right? When you insert VV4, there are so the question is, have you created a component? You can't create a component. Have you destroyed a component, right? So let's look at that case first. If V and the component towards the right, consisting of V4, V5, V6, they both belong to the same connected component, then the edge V, V4 will actually create a cycle. We know that. We have seen that earlier, right? So to avoid clutter, let me draw it separately here. So here is V, and I have something like that. I have this part. Now so if the two lower stars are actually or the two lower links actually are actually connected outside of the saddle, then inserting the edge V4 creates a cycle. So it's a creator, right? Right. So it's a creator. Let's go with that first. So let's say it is a creator. V4 is a creator. Next I insert the edge V5, which is also a creator, right? And I insert the triangle next. But this triangle now is destroying the cycle created by V5. So the so the new triangle you inserted and V5 are paired. And then you insert V6, which is a creator, and it is paired with the triangle you insert next. So at the end of this exercise, there is only one creator that is left unpaired, namely the edge V4. So the saddle is represented by the edge V4 and as a creator of a cycle. Okay, that's one scenario. The other scenario is if the lower links are not connected, right? So they are not connected. So in this case, when you insert an edge, this actually destroys a component. But which component does it destroy? It destroys the younger of the two components coming from left and right. So maybe the left component was created at a minimum M1 and the right component was created at a minimum M2. So the edge destroys the younger of the two and it is paired with that. So in that case, this edge is again, it's a destroyer, but it is paired with a minimum. Again, it is an edge that represents the event, right? So what happens afterwards? You insert one more edge, which is again a creator, and it is paired with the triangle, and then you have another edge, which is a creator, and it's paired with a triangle. So the remaining simplices in the lower star are paired locally. The only edge that between V4 remains is paired outside of the neighborhood. Okay, so the maximum is fairly simple now that we have gone through this exercise multiple times. So I will not draw it fully. When you insert the maximum, you create a component, so that's plus. And when you add an edge, that destroys, so the vertex is paired with the edge, and then you have a creator, destroyer paired locally, creator, destroyer paired locally, creator, edge, destroyer paired locally, creator, destroyer paired locally, and then a creator followed by yet another destroyer paired locally. And then finally you have a triangle to insert. This triangle, since in this case let's assume since we are working with 2D, this triangle will be also a destroyer. But who does it destroy? Which cycle does it destroy? There is no cycle within this small neighborhood that is destroyed. In fact, this cycle was created much earlier at some saddle. So you will have to go outside to find. So you'll have to go outside to go and find that saddle, which is the creator, and that's not too difficult to do. But to summarize, what we have seen is that for all the simplices in the lower star filtration, all of them are paired locally, except for the critical points, where for a minimum the vertex is positive and it's paired outside. The saddle, there is one edge which is again paired outside, and the maximum there is a triangle that is paired outside. Now we know how to find these pairs using the cycle search algorithm. So using the cycle search algorithm, we can also find the pairs of critical points. Right? So the two ways of looking at persistence are actually equivalent. Depending on the application, one is more beneficial or gives us more insight than the other. To summarize, in order to pair critical points, we looked at a filtration using lower stars. The simplices that belonged to the lower star of a regular point was paired with local simplices, and for the critical point, one of the simplices was paired with a foreigner, with somebody outside of the local neighborhood. And the dimension of the simplex, as you will notice, is related to the index of the critical point. Since you pair simplices of dimension that differ by 1, we obviously have the critical points that are paired also differ in index by 1. I mentioned that we run the cycle search to pair the simplices that lie outside the local neighborhood in order to find the pairs of critical points. Now, this pairing also tells us something about the earlier relationship we saw on the Euler characteristic. So we saw that the pairing of simplices corresponds to the pairing of critical points. So you can use this also to see the one-to-one relationship between the critical points and the simplices. So every pair of simplices cancels out when you look at the alternating sum. So all the local pairs do not contribute anything, and all the remote pairs of simplices correspond to a pair of critical points. So hence the Euler characteristic can also be shown using this pairing idea. So with that, we have come a full circle, and we have seen how the filtration can also be used to study Morse functions and look at the pairing between creators and destroyers, which is the central idea in this topic of persistent homology.